Hey everybody, this is Mr. Schultz here, back with you. We're going to take a look at lesson 3.1.2, which is how can I make a prediction? So we're basically going to take what we did yesterday. We're kind of trying to find these patterns and kind of write rules with them, and that's kind of the direction that we're going, is trying to write these rules or equations or expressions that help us make predictions about specific things. So we're going to use tables, graphs, and rules or equations to make those predictions. So let's take a look at this by starting off by watching this here.
National Geographic has a long history with redwood trees. We photographed 300-foot tall, 1,500-year-old tree that survived being cut. And it's the scientists that study these trees, this is their favorite tree. It's the most complex architectural tree on Earth that's known. But photographing it is nearly impossible. Spent a lot of time figuring out how to make this picture, and ultimately we ended up raising cameras up into the canopy. We made it mechanized. We put 3 cameras on a dolly. There's a gyroscope. Drop it slowly down, and also we're making a photograph. So what you're going to do is you're going to build a tree out of lots of pictures.
All right, so basically what we are getting at there is that redwood trees are ridiculously big. They're incredibly huge, and so we're going to use those as kind of a thing to try to make some predictions with them. So it says John found, and this is question 3-10. We are skipping question 3-9. And jumping straight into question 3-10. So it says, John found the data in the table below about his favorite redwood tree. He wondered if he could use it to predict the height of the tree at other points of time. Consider this as you analyze the data and answer the questions below. Be ready to share and justify your answers with the class. So it says number of years after planting. So you've got 3, 4, and 5 years, and the height of the tree is 17, 21, and 25 feet respectively. So so we are going to look at a few of these questions here. So the first one, how much did the tree grow each year? So looking at this here, well, at year 3 it was 17, at year 4 it was 21 feet, at year 5 it was 25 feet. So it looks like this is just a simple adding 4. So I'm just going to simply add 4 to this here. And then it says, B, how tall was the tree 2 years after it was planted? Well, this was 3 years, and it's adding 4 each time. Well, then in theory, I just have to knock this down 4 feet, and then I should be good to go. So if I knock 17 down 4 feet, I should be at 13 feet. The next question says, what about 7 years after it's planted? Well, this is only 5 years, so I'm just going to do the same thing. I'm going to add on 4 to get to 6 years and add on 4 to get to 7 years. So if I add on 4, then I should be at 29. If I add on 4, then I should be at 33 feet. And then it just says, how do you know? Well, I'm just adding and subtracting 4 because it seems like it's constantly growing by 4 feet. How tall was the tree the year it was planted? Well, same type of thing. I'm just going to back this up 4 and 4 and 4. So I'm going to back it up 4, which was back down to 13 feet. I'm going to back that up 4 again, which was down to 9 feet. Back that up 4 again, and that was 5 feet. So the year 0, so the year that it was planted, it hasn't grown in the ground at all. It was 5 feet tall, which you may think is weird, but it's actually a fairly common practice of trees to be planted after they've grown in like a pot or something like that. Estimate the height of the tree 50 years after it was planted. Well, you could go and add this all up and say, well, plus 4, plus 4, plus 4. Just sit there in your calculator and press plus 4, plus 4, and count until you get to 50. Or we could make some sort of a prediction here. So it looks like so if at 5 years it is 25 feet, maybe we could just say, well, multiply that by 10 and call that good. Maybe you could say, well, each of these is just growing by 4, so maybe I just take 50 feet and I times it by 4. A bunch of different approaches here that you might try. Let's try that 50 times by 4 because we know it's growing 4 feet each year. Let's just say that we know it's probably somewhere between 200, and then if we took 5 and we push this up by a factor of 10 to go from 5 years to 50 years, well, then we'd be at 250. So we're going to estimate that this tree is somewhere between 200 and 250 feet tall. Now let's jump to our book here, because in our book there is a good e-tool here. So we just answered these first few questions. So we're jumping down to question 311 now. So 3-11 says, John decided to find out more about his favorite redwood tree by graphing the data. Click in the lower right-hand corner of the graph to view it in full screen mode. So this little shape here in the lower right, you can click on that, and that'll make it go kind of full screen here. And then it lists the questions on the left-hand side here. It says, plot the point that represent the height of the tree over time. Well, we've got this 3 and 17 piece, but where is 17? This is going up by, I don't know what. Let's try 2. 2, 4, 6, 8, 10. Okay, yep, so it's going up by 2. So I'm just going to drag this point up to 17. Should be halfway in between. And drag this point up to 21. And look at that, it starts to create these lines. And I'm going to do that. Now we found a few other points. We found out what it was at year 2. So let's drag that up to that there, which was 13. We also found it at year 0, which we said was 5. So there's a couple other points here to plot. So at year 6, just plus 4, so 25 plus 4, 1, 2, 3, 4. And then we have our at year 1. Well, that's probably going to be right in between here. So we have 5 plus 4, which should be 9. Or, of course, you could take this 13 minus 4, which would be 9. So we see this kind of constant straight line. It says, and then B, or the rest of this question says, what does the graph look like? Well, it looks like a straight line. Does the graph represent a proportional relationship? In this case, it's really close, but it's not. Remember, if it's a proportional relationship, it has to start at 0. So it is increasing by a constant. It is a straight line, but since it's not starting from 0, it's not a proportional relationship. So this one is no. On B, it says, does it make sense to connect to the points? So connecting the points, well, it makes sense to. It's this straight line. It's just not going through 0, so it's not proportional, but it's definitely a line. It's not like there's like a zigzag or something weird or a circle. So yeah, so I think it makes sense. Moving down here to part C, it says, according to the graph, what was the height of the tree 1.5 years after it's planted? Well, the best part about graphs are that you can just go over to those points and find them. So on the x-axis, I'm going over to 1. Then I just need to go halfway between 1 and 2. Then I'm just going to slide up and try to find that point there. Well, it looks like it's about halfway between 10 and 12, so that's got to be 11. So predicting that it's going to be about 11 feet tall at 1.5 years after it was planted. Now it says, can you use the graph to predict the height of the redwood tree 20 years after it was planted? So 20 years. Well, my graph only goes out to 8. And on our previous test, I know that a lot of you said, well, no, you can't because the graph stops. But look at graphs. I can just pinch zoom and look at that. It goes way out now. It goes way, way out. In fact, I could find out what it is at 100 years. Or I could just keep going out now at 200 years, 300 years, and so on and so forth. So even though you can only see a section, it actually does expand out from that. So at 20 years, well, I can't quite see this line really, really well, but I could make an estimate, kind of go up here. It looks like it might be somewhere, maybe somewhere like there kind of makes sense. So I'm just riding up here, then just going to kind of extend the straight line out until I think it's around 20. So here I might say it's somewhere about, well, if this is going 50, 60, 70, 80, 90, 100. So 50, 60, 70, I might guess it's about 80 feet. Maybe somewhere around 80 feet, which would fit with our rule that we think from our previous section here. I'm just going to write down a few of these things now too. And this, of course, decided to not save my spot. So here we said, we said, can you use the graph to predict it when it's 20 years after it was planted? We were guessing that it was about 80. We said that you could, because you just keep extending that line. You just keep extending that out, knowing that it keeps going and going, even though I don't have more data. That's some of how I'm making a prediction. This is how a lot of predictions are made. So like all your predictions that people are making about like COVID virus or about all that different type of stuff, this is exactly what they're doing. They're plotting points. They're looking for what is the data doing, and then trying to follow that scale and say, how might that be changing? Now, obviously, there are other factors there. What if there's a forest fire? Well, then that tree is probably not going to grow. It's probably going to burn up. So other outside factors, but in this example, we're just assuming kind of normal growth the whole time through. So we're thinking that it's going to be roughly 80 feet, and we just kind of did an approximation there. Okay, so on this one on 3-12 says, John is still not satisfied. He wants to be able to predict the height of the tree at any time it was planted. So find John's table. It is on the e-tool. So you'd have to like take a snapshot of it and write in there, but I don't think it's very clean. So this might be something that you just want to hand draw and extend it to include the height of the tree in the 0 year, 1st, 2nd, and 6 years. So I'm going to take a second and draw a table quick. All right, so here is the table, and we had those given values. So then we just had those ones that we're going to fill in. So it's increasing by 4, or if I'm going backwards, it's decreasing by 4. So decreasing by 4, decreasing by 4, decreasing by 4, and our table should be good to go. So if I'm going backwards here, I'm decreasing by 4. If I'm going to the right, I am increasing by 4. So I could keep going with this table. So let's see what this next one says. So in part B, it says, and we didn't play the silent board game yet, or in this lesson, so you can skip that line. But in part B, it says, write an algebraic rule for the data in your table. Be sure to work with your team and check that the rule works for all of the data. So basically, remember yesterday, we had these tables and we were trying to write rules. We were trying to write something that we could use to start to make accurate predictions on the data. And then once we have a rule, I want you to use that to check out your prediction for the 50th year and see how accurate you are. So going back to this table here, we are going to write some sort of rule. Well, we know that it's increasing by 4. So somehow we need to say that this number multiplied by 4 is netting us this number because it's increasing by 4. Every single time I'm adding that 4. That's a thing we found out from yesterday, was just that every time we're increasing something by a constant number there, we can basically just say that's 4 times by whatever number it is. But that doesn't quite work, because if I try and do 4 times by 1, well, I'd get 4, I wouldn't get 9. And if I do 4 times by 2, I would get 8, I wouldn't get 13. So just taking it at face value, I'm getting this pattern. It's just times by 4. And what is it? And you might notice this. What is the change here? Well, from 0 to 5, it's plus 5. From 4 to 9, it's plus 5. From 8 to 13, it's plus 5, plus 5, plus 5. So what's actually happening here is we're saying multiply whatever your year is by 4. So if my year is 5, I'm going to multiply that by 4, and then you'll only be 5 feet away from the height. So to get that extra 5 feet, I would just need to add that constant of 5. So my rule would be 4x plus 5, because I'm growing by 4 feet each year, but I started at 5 feet. So I need that last little 5 feet to grow that, to make up for that difference there. So now here, if I want to make that prediction, going back to this slide, if I think my rule is 4x plus 5, let's see if our prediction for the 50th year is accurate. So we just take this 50 and we plug it in there. So now I've got 4 times by 50 plus 5. Well, 4 times by 50, we said that was 200. If you don't know that, you can plug it into your calculator. And then I'm just going to add 5. So I'd end up with a solution of 205 feet, which seems to make sense because we said that our prediction was 200 to 250 feet. And that's just because we were just barely off by that small amount of 5. So fairly close. We were in the right range, but we're just a little bit off there, which is great. This is a pretty good prediction here. So when writing rules, you're looking for how much is it increasing or decreasing by every single time, and then you're kind of looking for what is that starting value. And so tables are great for writing rules or equations, because you can see what's that increase or decrease. And then you just need to find out what's that starting value, and that starting value is what's helping you find out, do I need to add or subtract something onto whatever I am multiplying. And that's it. You will have your review and preview tonight, so take a look at those problems, and that should be it. Have a great rest of your day.